Very welcome to all of you for joining us on the session today. And today's topic is engineering bioinks to fabricate physiological systems. This is a part of our series that we've had this quarter, and we've had sessions before this that include skin bioprinting, understanding 3D printing, as well as the precision medicine applications, and so on and so forth. This is one of the sessions or one of the series that we have. Following this, we have a few more sessions. A recap on the previous session, I explained to you what bioprinting is. With what bioprinting is, I've also added up and explained some basic example, a simple model that is skin that is to be printed. And from there, now we're going to understanding what bioinks are, what is the whole process of development of a bioink, what are the kind of studies you need to do, and how you can proceed. So I'll share my screen with all of you now. All right. So I hope everyone can see my screen. Like I said, the topic is engineering bioinks to fabricate physiological systems. And my name is Aishwarya Shukshiru. I'm a technical specialist at Alton Technologies. Talking about us again, a quick intro as usual. We are a 3D innovation platform company, and we work with several software, several machineries. Say example, CATIA for 3D designs, MSC software for simulation, CFD modeling, Stratasys for plastic printing, which is quite varying in terms of its applications, say in terms of aerospace, in terms of healthcare, in terms of institutional studies, etc. Then we have RTech 3D, which is for 3D scanning, Dassault Systems, which is Biovia, and Cellink for life sciences. So Cellink Life Sciences is again into 3D bioprinting, like I explained. We also have several sections in it, and I can go on explaining about that as we proceed. We're a decade or more old company, and we have been establishing ourselves and setting up foot in the industry, and we have quite a large set of clients, partners that we work with. And since I told you our solutions are not only specific to life sciences, we're also into in general healthcare in terms of aerospace and defense, automotive industries, consumer products. We have a very diverse portfolio, and we have a team of people that works or that work with several sectors and several groups. In case you know somebody who can get some benefit out of us, who can learn from us, do follow us, do like us on LinkedIn and visit our website. Now I'll come down to the actual story, which is how did this whole idea come in? What are the challenges we are facing, and how we are proceeding towards creating, possible solutions for existing problems in terms of research or in terms of any other factors. So, like I mentioned before, there is a lack of organ transplants when it comes to our current situation. Although there is good amount of medical equipments and good amount of research and development happening in healthcare, there's also certain areas which are challenging to attain, like the organ transplants itself, and how we all have to struggle in order to get even the most basic organs. And even if we get these organs, we have a sort of immunological response that happens because of any sort of rejection, any sort of issues. From there's also the waste due to wrong testing methods that we adapt. And when we use these wrong testing methods, the time required to proceed with anything kind of alters and changes, and it prolongs quite a lot. Then comes the lab to shelf time. So there are a lot of drugs that are developed. It has not reached most of us because failure maybe in one of the trials, or false positives or false negative results that we get. And you would have certain set of technologies or certain steps adapted to bridge these sort of gaps that exist in terms of the research and development in technology. So I'll come down to our main essence of this session, which is biomaterials, also called hydrogels, and so on. So there are some definitions that we need to remember. One is a biomaterial is basically a material designed to take a form that can direct through interactions with living systems in the course of therapeutic and diagnostic procedure. So when you talk of any sort of material, we are concentrating on biomaterials. So basically, the resources or where it is attained from is actually biological resources, and these biological resources are the main factor for creating something. The materials are actually designed to form any sort of structure, right? So you get these, you obtain them from, say, chitin or alginate, or even the most basic materials that you get are going through a lot of processes in order for us to use it in general. So then comes bioinks, right? This is what I have been saying quite often in our sessions, and even in this session, I've used the word bioink. So bioink is actually the whole idea of a bioink is cell laden biomaterial. So you would have a material which is biocompatible, yes, but it should also allow the better cell viability. It should give a good friendly environment for the cells to grow in, and that's how bioink came as a name in terms of additive manufacturing in general. Defining what biocompatibility is actually the ability of a material to perform with an appropriate host response, right? So when we have a host that is a main ground, and then you have any sort of material, right? There should be a sort of interaction which should be more on the positive side. There should not be any harmful effect when I use one particular material on the biological system or the biological environment around. So that's the idea of what biocompatibility is. And now this depends on the application, the kind of cells you want to use, the kind of area you plan to use it. And this biocompatibility is a widely used term, not only in cell biology but in other sectors as well. Say, example, there are quite a lot of materials which are used in healthcare, and they vary depending on applications, depending on strength, and a lot of other factors. So in healthcare, the idea, the whole sectors or what you use there would be maybe implants or substitute materials or materials that are in direct contact to your body. So anything of that sort in entirely which holds in medical devices is where healthcare can come in. So you have maybe PEEK as a material, you would have polypropylene, you would have then you would have PC or PP or vinyl material. Then you have also the alginate materials, which we'll talk about in future, and then we have titanium. So these are all materials which are called biocompatible itself, uh, because they do not cause any sort of adverse effects to the body when in contact with it, right? So you would have these materials in such a way that they do not cause any harmful effects, and they're also in direct contact with your internal, say, invasive or externally to the body. So these are there is a quite a large amount of work and research done to use these materials for any sort of application. So we spoke about how materials are in general, but the concept of material sciences again came in from the idea of tissue engineering itself. So tissue engineering is a interdisciplinary field, like I mentioned, and uses the principle of engineering and life sciences towards the development of any sort of biological substitute. Now, the whole definition of tissue engineering was to restore, maintain, and improve any tissue functions, right? So these tissue engineering concepts holds in a lot of materials, a lot of aspects to it. Say, one being the main aspect, that is a scaffold. Then you have the cells which you're selecting, and then you have your chemical and physical factors. So in the scaffold, we say we have defined already that porosity is important, The cytocompatibility and the tissue compatibility is important. The bioactivity is essential. The cell attachment and migration are important. And then you have the mechanical properties. Following that, you have maybe the cell type. So in the cell type, you would do or take care of selection of the cell type, more relevant cell models, interactions, signal pathways, integration of flow. And I think chemical and physical factors would just be the nutrition media, the environmental factors like the temperature, the humidity, the pressure, and few other aspects to consider. So, when we talk about creating a scaffold itself, actually requires the need for material sciences or the study of materials to come forward for your application. So, when you talk of the material science aspects, you're actually looking at what is the material you want to use, how well am I going to create my scaffold material, and how can I then incorporate this in terms of creating a subsequent tissue or a material that is more in contact with the body, or even generally, right? So when you talk of tissue engineered biomaterials, you will consider strength for sure, because I am trying to create something which is a sort of an infrastructure, a sort of scaffold that can hold cells. So it needs to have, or it needs to impart strength. Then there needs to be elasticity. Elasticity is essential in cases where you're using and creating very elastic sort of materials, or materials which can deform and come back to its original structure and shape. And then you have biostability, which is important, which is again the whole and soul of biomaterials. Lack of toxicity. For example, a material is being used. If it causes a toxic effect on the cells, and there is no point of it being called a biomaterial. Or it can, see, there are always materials which are biocompatible, or biomaterials in general, but we need to know what is the right concentration of that material that might not impart toxicity to the cells that are growing in it, and yet providing the required biochemical factors. So magnetic property is also something you can incorporate. Now this depends on what application you want to go for. So I am just specifying in general what are the general points that we usually talk about, or what we usually consider. Host response, and this is honestly very very important, because if you are calling something a biomaterial, and you're using it for a certain application, you need to understand what is the host response. If the response is on a negative side, there is no use of having that material. But if it's something which actually induces a sort of a better biochemical production, or better anchor, or better ECM production, then it actually comes in line with the application that we want to get along with. Then you have mechanical stimulation. So these materials are again physically placed somewhere and being put somewhere, and that needs to allow the surrounding cells, if it comes to regeneration, to impart these functions and to produce this right set of biochemicals and biological factors. So there's a correlation between the biocompatibility and the printability. So if you look at a material which is highly printable, there are chances that the biocompatibility might be less. So there is a sort of a direct relation, a proportionate relationship between the biocompatibility, that is the cell viability, and the printability. So the higher the printability, there are chances that the biocompatibility might be lower. So we need to get that ideal point, the fixed point, which can compensate for better printing, as well as allow for the cells to grow better in it. So if you have a very high level of, say, protein or polymer content in your material that you're using, that might hinder in terms of both physical and chemical aspects of the cell growth. So optimizing these are quite essential, quite crucial. And when you're looking at tissue engineering itself, it is very important to consider the spatiotemporal arrangements of the material along with the cells. right? So while you have your main principle in hand, you also need to make sure that the actual physiological aspects of a particular application needs to match with it. So the spatiotemporal arrangement will just be what is the kind of structure, the geometry that my anatomy is going to attain, while keeping the materials and the cells in line, keeping time in consideration, right? So having to do using our general conventional methods of tissue engineering can really affect in terms of geometry, in terms of time, in terms of materials. So that is where we have kind of come down to using different and new techniques. And when you keep spatiotemporal aspects in mind, you will have to see maybe the material being injectable, having appropriate mechanical, biophysical properties, the release of the biomolecules that we want, then the degradation, right? So the degradation and toxicity. Whenever a material degrades, there are chances that it might leave out parts or break down into something that is toxic. So if you are doing a biomaterial studies, you have to make sure that the degradation time is taken care of. While the degradation is taken care of, there is no any toxic effect or toxical effect on the cells. Then important factor, the architecture, morphology, and uh, the requirement of the respective biomolecule that you need. So when we talk of the architecture itself, then we would, see what is the best method to go about in terms of creating that specific architecture and giving the main anatomy or the main design. So, in all, what tissue engineering is not only just biomaterials, not only just biomolecules, it's also the architecture, which can really help in terms of cell growth, maybe 2D or 3D, and eventually the whole principle beyond this is to stimulate the niche cells, right? So, whatever you create in your biomedical space, inclusive of biomaterials, biomolecules, and architecture, is the whole composition of how your bioinks or how your biomaterials to be used. So there is intensive amount of research that is going on right now in terms of selecting the right biomaterial, looking at the chemical composition, making smarter biomaterials, that is combining materials which is low in viscosity with a material high in viscosity, creating stable materials, making materials which can be best incorporated into the body, say maybe stent studies or any sort of CABG or anything. So any aspect of healthcare requires extensive or intrinsic knowledge of biomaterials. So that's where the whole idea of 3D bioprinting actually came in, because here architecture is something we need to see. We also need to see the biomaterials and eventually the biomolecules. So biomolecules is again something in direct consideration, taking your cells, taking your biomaterials together, right? So I will define 3D bioprinting for you again. It is a form of additive manufacturing that uses cells and other biocompatible materials as ink. So here you're trying to print the living structures layer by layer, which mimics the behavior of natural living systems. So when you look at uh, 3D bioprinting, it again imparts or uses tissue engineering as its main crux, and it also uses a technique of 3D printing. 3D printing is plastic printing again. And again, here the components are going to be the same as tissue engineering, except there will be some modifications. Cells, bioinks, culture media. So when you come to the point where bioinks are used, that's where we'll have the emphasis most on. Uh, this understanding the steps which are necessary are very whole selection and characterization of materials and when it comes to bioink development. So, like I said, the steps are anatomical data or MRI scan or a 3D scan, and these combined or individually can give you the right geometries that you need to use. So you'll know, okay, fine, if I'm taking skin, my liver, or any other thing. So each of the cell types have a very different arrangement of cells within it, and you'll know more through histologies or old datas where they have completely specified and defined the arrangement of how the cells are, what are the essential components of it, etc. So this step entirely is called imaging, and with imaging, then we go to 3D design. So whatever imaging you have will give you that data, but I have to convert it into a 3D format, which is in the XYZ direction. And here's where you'll design. A crucial section is material selection, which I told you already about, and the cell section. This is the whole bioink development phase, and this phase defines your whole bioprinting process. So, if I my end result will be hampered entirely. It be the aseptic environment, so the environment in which the cells are growing, or it may be material aspects of it, where the material might be contaminated, it might not be biocompatible, it might not impart the right cell viability, it might not allow better biochemical synthesis, and etc., and so on and so forth. So there is extrusion based methods and DLP based method, which I mentioned before, and I also recap that for you. And then we have the UV curing or the cross linking phase. Then we have incubation, and then there is applications or in vitro tests. So this constitutes entirely of bioprinting, which is a broader definition, but each of these sectors require their own separate set of studies. So there are people who are into individual sectors of it. There are some who are into the imaging aspects entirely, some into the design aspects, some into just the material sciences, some into only cell biology. And then you have just the technique or the technology used to print, following that cross linking, that is a light, what sort of light is impacting. Incubation is again a whole different phase. So it's a very multidisciplinary field, because you're using different concepts put together which have to work together to create a successful model. uh, so when you're talking of the considerations when developing the bioink for 3D bioprinting, so they are more in line with what I have mentioned to you as the steps in bioprinting. So here you will have the choice of the materials, say whether they're easy to print. If they're easy to print, are they even compatible with the cells that I want to choose? So you have quite a wide range of materials available, and choosing the material is very crucial. So we have sort of a guide with us which can actually help you understand for which type of tissue can use what material. So say if I have to create skin, and to create skin I need to use maybe alginate material or cellulose material in combination. And with that, if I need any other biochemical factors, what has been the nature of the fibroblast cells when it came to printing in that material, and what is the results that you attained. So you will get a good flow and a good understanding of bio ink development or bio inks in general, because uh, Cellink is not only a 3D bioprinter company, it is also into bio inks. So they actually started off with preparing commercial grade bio inks used for bioprinting, and that's how they also created these bioprinters. So it requires a deep knowledge of materials to actually use any machine. So it's quite a sort of complementary process when it comes to bioprinting. Cell type selection I have mentioned. Method of printing, right? So the method of printing can be, say, extrusion based printing, DLP based printing. So that's where we have the Incredible, or we have the BioX, and then we have DLP based printing for um, Luminex Plus, which is for creating some sort of microfluidic structures or rigid structures or complex structures. So why I mentioned these two printers, or why I mentioned that method of printing is important. So if I'm using extrusion based printing, I need to have a very different set of parameters I need to use. Say there will be a classic set of things which you need to see about: biocompatibility, the rheology, the flow properties. But the rheology and flow properties are dependent or different when it comes to what technology you're using. If I'm using extrusion based printing, I have to take care of the viscosity a lot because it is going through some mechanical stress for the printing process to happen. Then I have Luminex, which is just a resin bath which consists of your material. Although after cross linking, we don't know what could be the mechanical properties of it, or how well will it swell or not swell. So depending on what type of technique you want to choose for your method, for your way of printing, you will have to make a decision whether I want to go with extrusion based printing or DLP based printing. The tissue structure, which is important, like I said, the anatomy and the model, incorporation of growth factors and any other differentiating factors if required, capability, the cross-linking intensity. So if I'm developing a material, I would rather develop it specific to one machine, because I would have, uh, say, example in terms of QC itself, right? Quality checks or any check, you will use one particular machine to follow the rest of the steps. So it's crucial to do this bioink development when it comes to finding the right parameters in the machine. So I want to know if I have a better temperature control, if there is a better environmental control, is pressure, is there good speed when it comes to printing, am I able to stop the print while I'm carrying out the process, can I modulate the pressure while I'm doing the printing process. So all of structure, then you have figure. Then you have your triangle, and then your rectangle. So then comes the cells or the chemical factors. I have mentioned to you about the types of figures, which is extrusion printing or rigid light process. So you have pressure assisted filament printing, multiple models or multi. is your digital diagnosis. Okay, and the audio is on. So when it comes to biocompatibility process, yeah. So I hope everyone's able to hear me. So here we have extrusion and electrolysis, right? So I give you some examples. Say the targeted radiological time development environment. So here what they've done is they have considered bioprinting process where they're concentrating only on the radiological aspects. So when you consider the radiological aspects, you will see maybe the systemic correlation with okay, so this is strongly influenced by the temperature profile, and the duration. Okay? So when you talk about bioprinting itself, it is influenced by a lot of factors. So you have gelling mechanism, mechanical stability, cell adhesion, and printability. So you have to test whether these 4 points or at least these points are useful when it comes to printing. So
Ashwarya,
then you have Very sorry about that. There was some technical issue here. Yeah. So you have uh, sodium alginate, carboxyl methyl cellulose, and gelatin that were used. So when while using these materials, you're actually considering, say, whether these materials are complying to maybe the gelling mechanisms or mechanical stability, cell addition, and printability. So when we did the tests, or when they did the whole characterization process, they had to do the hydrogel characterization where homogeneity was considered, the density was considered, the rheology was considered. And then you have the printing process. In the printing process, they would check for the temperature sweep, the processing time, the nozzle dependency, and the gelation kinetics. Next is the post-print studies. In the post-print studies, you check the cross-linking and the thermostability. So the rheological studies will definitely include concepts like taking the ultimate strength test, doing the Young's modulus test, the stress strain, basically the stress strain tests. You will have then maybe the general strength of the material, etc. So these have to be considered when it comes to printing. Biomaterial development, again, the whole other example which I find is my favorite. Here you're doing the optimization of extrusion based ceramic designs. So your materials are used for bone grafts, say alginate, collagen, silk fibroin, gelatin and its variants. So when you're using for bone grafts, you would have to go with like all of these materials and then consider what material is the best one that you could choose, say hydroxyapatite or tricalcium phosphate or biphasic calcium. So they are actually available in beads, coatings, injectable cements. So you can, if not, right. So when I said we were talking about healthcare and applications as well, we don't always have to consider using cells in them. We can sometimes also go with just using the material as a graft material or as an implant material. So this is a case where they've done that and they have taken hydroxyapatite mixed with the thermoplastic. So the thermoplastic material is mixed with it so that you can adjust the degradation time. We don't want certain materials to degrade too soon within your body because we wanted to impart the osteoinduction and conduction around it when it comes to bone. Right? So this example is where they've again used a CAD file model, sliced it into layers of different infill density. You have your bioink preparation that is done. You have again the layer by layer printing. Now, when you're doing the layer by layer printing, you are testing it at different infill densities, say 50% or 75% or 100%, and these will help us understand the mechanical aspects of our print. So here you use maybe SEM analysis. You would also require sometimes using TEM analysis. When it comes to using only the biomaterials or testing the biomaterials property, you can use AFM. You do NMR studies if you're using any sort of solvent materials while creating this, this sort of bioink. So this was wholly optimized for a patient so that they can use it as a graft for the patient and do a studies of that. So here there is a patient who has this radius ulna fracture, and they're trying to now take respective designs, get the recombinant images out of the person, reconstruct the image, use the CAD model, printed using maybe using basic plastic printing, and if the plastic printing is able to give you the specific model, try the same thing with bioprinting techniques using hyaluronic acid slurry and so on and so forth. So while you're doing this printing, also the nozzle dimensions are important, the print speed is important, material reproducibility is important, reconstruction, graph to defect distance, then printed part dimensions, all this have to be considered. So then you have pentanoid, right? So this is another example where they're doing the cross-linking test only. Right? The main emphasis is cross-linking, and Again, printing is also another factor when it comes to maybe shape fidelity, etc. So they've used pentanoate functionalized hyaluronic acid. They've used dithiothriotol, which is a cross-linker. So they've tested for shape fidelity, the viscosity, the yield stress, the storage modulus, the cell viability, the printability. So cross-linking has a very, very crucial factor when it comes to the cell viability, because too much of UV light exposure can really reduce the cell viability. Too less of UV light cannot make your gel-like material strong enough. So all these have to be considered when you are developing your biomaterial. So again, those two examples I think have given you some basic insight of what I'm trying to say. Uh, um, Again, there are a lot of papers, a lot of publications and research materials available on our website, which can give you clear examples, clear understanding of the processes involved in terms of bioprinting, bioink development, and biomaterial synthesis. So here you use Incredible Plus, BioX, BioX6, BioMDX Plus, and LumenX. So they're all depending on the complexity of the machine, the temperature controls, the build volume, the build dimension, the precision, the technique of bioprinting that you want to use. And I've also mentioned to you about BioVia, which is a simulation software. It's also called BioVia Discovery Studio. So the capabilities would be protein engineering, antibody modeling, simulations, X-ray analysis. So if you have any doubts on this, you can always join my colleague Divya's webinars and presentations, or directly contact her for any sort of clarifications, understanding details, so that you can understand how BioVia can also be used with bioprinting. Um, our basic vaccine development also has incorporated using in silico models along with bioprinting softwares, both used together in order to do your clinical test, drug development, drug testing, etc. So I think this is quite straightforward, and it has a very diverse set of applications, which I'm not going to get into. And that's all for now. Thank you so much. Until then, I will just share about the bio quiz. So, the question now, or the question two, which we would say, is what are the essential properties when it comes to bioink selection? So, first is printability, second is temperature, third is shear thinning, and fourth is speed and pressure. So the rules for this process is to first answer in the comment section, subscribe to our YouTube channel, now share this video on all your social media platforms, tag a minimum of two friends to challenge them, and you can use the hashtags selling, hashtag altum, hashtag bioquiz while you're sharing this post. So when you get when you answer all of these questions, like say about 3 or 4 questions that we've already put or plan to put in the future, we will select about 3 winners, and these winners will be announced on the 5th of October. So the person or the 3 people who win will get the Amazon gift voucher, which is 2,000. Sorry. So my session was interesting, and now I will take any questions from your end. Are there any questions here? Feel free to type down your questions here and I can answer them for you. So yeah, there's also the feedback form which has been put here. Questions? I don't see any questions. So I'll just maybe say a few old questions that I have come across. Um, saying what is the effect of contaminated bioink material, right? Contaminated bioink material can definitely not be used or mixed with cells when you have to use it in terms of bioprinting. Um, Bioprinting requires rheological studies, viscosity studies, and also chemical analysis and chemical processes to deal with it. I don't see any questions for now, so I guess that's all for now. I'll end this session. Sorry for the small technical glitch in the middle, but I hope uh, our content, our technical, contents are in line with what you require. And please join us on our next session. Thank you.